Hello, everyone. Welcome to this session of the MLOps conference. My name is and I work as an applied machine learning engineer at Algorithmia. Today, I'm happy to be here as a volunteer for the MLOps community and introduce one of our many brilliant speakers. Before we start, I'd like to remind you that if you have a question during the talk, please feel free to post it in the chat as we go. When the presentation ends, I'll be asking those questions to our speaker. And now in this session, we have Talal Riaz from Yelp. Talal is a software engineer with the ML infrastructure team at Yelp, and he has a PhD from the University of Iowa with a focus on randomized and distributed algorithms. And today he's going to be sharing how they built an Elasticsearch plugin within Yelp's model platform and their lessons learned in making their pipelines more performant. So please join me in welcoming Talal, and now I'll pass the microphone to him.
Yeah, hi everyone. Thank you, Asi. So I'm Talal. I'm on the machine learning infrastructure team at Yelp, and let us begin. Okay. So today I'll be talking about quick model serving in ranking systems. So as I mentioned, I'm on the machine learning infrastructure team. So let me first give you an overview of what the machine learning infrastructure looks like at Yelp. So we've got something we call the model platform. There will be another talk with a broader overview of this that focuses on diagnosing failure modes. It's given by Jason and Daniel, and it'll be tomorrow at 2:45 Pacific. So keep an eye out on that if you're interested in that. But for this talk, we will be focusing more on just one part of this picture, especially the plot highlighted in yellow. So if you look at this picture, you can see there's two subtrees. There's one with the model trainer heading, and then there's one with the model inference heading. The model trainer part subtree is the offline distributed training part of it, while the model inference subtree is the online model serving half of it. And to give you more detail, the left half of this subtree is powered by PySpark, whereas the right half is powered by MLeap. Both are open source available plugins, available projects. Now, a typical development workflow that you will see using the model platform starts off in the left subtree, and it ends up in one of the leaf nodes in the right subtree. So we're either going to have people, what it usually starts off with is an engineer, an ML engineer, prototyping in a Jupyter notebook with a model, evaluating it and noticing it has good performance, then moving this over to a batch job, which trains and stores this model. And then this model is used possibly in some kind of online manner. And the three modes that we let you use are a Java microservice, a Flink app, and as we will see later in this talk, an Elasticsearch plugin. So with the context here, I want to say that we start off this talk having done completed the rest of this picture, but this specific path was not done. So if you wanted to use your model that you've trained using the model platform in Elasticsearch, this did not exist. And for the rest of this talk, we will focus on this pathway. Okay, so let's go through a simple exercise with some background on wanting to train a model using some data that I have available. Let us assume that we've got a feature store that gives us all the features we're really interested in. In real systems, it's quite likely that your data is coming from a feature store and a data store, and maybe there's some unstructured logs in S3 and your data is also coming from there. But for here, let's just assume that we have all the features that we need in a feature store. The use case is Yelp and we're trying to power our search. So the kind of features that I've highlighted here are features related to a business. So for example, its location, its category, is it an advertiser, what its rating is, how many reviews does it have, and so on. And maybe I want to train a simple logistic regression on this data. So it looks pretty nice, right? I get the features directly from my feature store, and I can quickly train my model on it. But hey, this isn't right, because that model that I'm using, that logistic regression model that I'm using, it actually expects a feature vector as its input. So really what I need to do is I need to take that input data, convert it to a feature vector, and then send it into my logistic regression model for training. As you might have noticed, I've sneakily gone from the features to calling them base features. And I'll give you more detail on why I'm calling them base features later. But what I've done is I'm able to train a simple logistic regression model. I evaluate it, and as it turns out, it's just not doing that good of a job. Like, I've evaluated it, it's not doing a good job. Maybe I should help my model do a bit better. So what I end up doing is I create a new feature, and it's a logical AND of saying, does the business have a rating more than 3? And does it have more than 30 reviews? And if it does, this new feature is true, and it's false otherwise. And we notice that the model is starting to do a bit better. So maybe we're on the right track. So I'm going to start adding more and more of these features to help my model train a bit better. What ends up happening is that we get a large number of these features that really improve the performance of the model. But we've also now got hundreds of these additional features. And this is something that we have to deal with. So notice how I call the original features as base features. I'm going to call all of these new features derived ones. And the important thing to note is that it is just not worthwhile storing these in any kind of feature store or data store. These really are just features that you want to produce as part of your model training pipeline. The issue happens when you've got a model that you've trained, and now we want to actually use it to make predictions in an online system. So even though we would get our base features for free, so by that I mean we've got a feature store, and we can route those base features directly into our Elasticsearch index, which is where we want these features to be. But even though those features are there, we don't get these derived features for free. Elasticsearch, where the plugin we're going to be using, it's a Java plugin. So as I mentioned before, our training is done using Jupyter notebooks, using Python. And so all of this code that we wrote for building these new features, we need Java analogs for them. And if we don't have those, then what do we do? So this is a situation we find ourselves in. We've written some feature derivation code that does not have Java analogs. And we need Java analogs because we want to serve them in a really performant system. The system of choice is Elasticsearch. So at this stage, we enter a fork in the road. Our model training was done using Python in a notebook. It's possibly later on converted to a batch, but that batch is also, it's a Python batch. All of our model training code is usually Python. Code must be deployed as a Java plugin. We just can't reuse our model training code. So at this stage, we are faced with two options. There's just two different ways we could have solved this. And I'm describing right now the situation as it was a few years ago. So we have option one, which is we rewrite the feature derivation code using Java code. So those feature transforms that we wrote, we rewrite them with their analogs in Java. We build our own serialization format. And lastly, but really importantly, We ensure that our specific transformation is written once. So we're using really good practices, making sure that we don't reuse our work. So if you're doing something like a logical AND, we did use, even back then, we did use parameterized ways of computing those things, those features. But this is really difficult because it entails a lot of work on our own. The other side of it is we use some open source libraries. So let's say we find an open source library that has a lot of predefined feature transformations. This open source library needs to have Python hooks as well as Java hooks, because we still want our ML engineers who are more comfortable using Python to be able really easily be able to train. This library needs to ensure parity between the offline training, the offline train model, and the offline Python feature transformations, as well as when that same thing is done in an online serving manner using Java. And finally, it needs strict performance guarantees. And this part is important because we had really strict performance guarantees when it came to deploying for search, for our search team to power the Yelp search. So at this point in time, can anyone guess which option we went with? I'm going to answer this for everyone. If you guessed option 2, you guessed wrong. We actually went with option 1. And there are a bunch of reasons, but the most important one is that when this decision was made, there weren't many open source libraries that were mature enough to be able to be adopted this easily. And this would require a lot of work on the part of our ranking teams and our search teams to be able to do something like this. There was also always a big question mark where you use a big open source project, it might not be fast enough at the end of the day. So a lot of expenditure might not work out so well. The picture changed after we had a machine learning infrastructure team, because now we had, not for this use case, but for other use cases, we had built a model platform that solved all of these questions. We were using PySpark ML for a rich library of predefined feature transformations. We knew how to write code for Python with PySpark hooks, as well as for Java with MLeap hooks, where MLeap provides a nice, quick runtime for making feature transformations. And MLeap provides parity between the offline training and the online serving part of it. So a lot of these questions were solved, and we had already deployed them in production systems, but just not for Elasticsearch. The final part of it was, does MLeap runtime still give us the strict performance guarantees that are required for powering search? Now, this is something we did not know, but at this point in time, we had so much success everywhere else that we were like, okay, this is just one pathway. We've already done this a few times. We can do it. So we go forward with just full support and going and implementing this, extending our model platform to the Elasticsearch plugin. So let me show you what the picture now looks like. So remember that our picture that we had earlier on, where we've got all of these feature transformations that we wrote ourselves. The same engineer wanting to train the same model, what they would use is PySpark transformations. And we've also added some of our own to expand the library that PySpark provides. So instead of all of those transforms that we wrote ourselves, you would use pre-existing transforms provided by the library. So this is what our pipeline becomes. It becomes a pipeline object with a bunch of stages, and all of those stages are predefined feature transformations. Now, once you've trained this model, it automatically, you get its evaluations and all of its metadata stored to MLFlow. And also we provide, like, you can optionally also store your model as an MLeap bundle directly to MLFlow. On the other side of it, when you wanted to deploy it to Elasticsearch, this is how the situation would change. Your features would come directly from the Elasticsearch index. Your model, which had been stored as a serialized MLeap object, would come back directly from MLFlow. And you would get the entire pipeline that includes all of your feature transforms back. This online serving part is completely powered by MLeap. All of these are MLeap transforms, which we've expanded ourselves, just like we had done with the PySpark transforms. And this is what the picture looked like. It was a big shift in three different ways that I really want to highlight. First off, our engineers no longer had to think about the model as being separate from the feature pipeline. You can think of an ML model as being the model itself, but also the entire feature generation pipeline that goes into making the features ready to train the model in a better way. The second part is that engineers can focus completely on training their models. If they have trained a model and they've serialized the entire feature pipeline, then the other half of it, which is the online serving part of it, they don't have to write any of that code again. In fact, as long as you can ensure that you have the base features ready in both locations. So you've got the base features, you've got the same base features that you had when you were training in an offline manner in your Elasticsearch index, you would not have to worry about this at all. And finally, this paradigm shift allowed engineers to be able to go from training a model to deploying it and running experiments with it in a matter of hours. So it improved development velocity, it improved experiment velocity, and as we will see later, that helped us a lot in many different ways. But one thing, if we go back, is this last point that I put a question mark over earlier on. So remember that there was a question mark over how fast this could be. And this is one of the pitfalls we entered into. It turned out that we had really strict, let me give you a bit of an overview on how strict the performance guarantees needed to be. It was less than a millisecond to score a single candidate. And we had to be at most 50% slower than option one that I described earlier, which was the status quo. Otherwise, you could bring the cluster down or force an expensive upgrade to a large cluster. And this has at the risk of potentially derailing the entire project. Were we fast enough? We actually were not. We were about 100% slower than option one. And the reasons for these are, like, a personal opinion is any generic solution that we adopt, like MLeap, which has to deal with all kinds of models and all kinds of feature transformations and any number of ways of hooking them together, it's never going to be as fast as a generic solution, as a specialized solution like they had in option one. But we didn't have to beat option one, we just had to be close enough to reap all the other benefits that this kind of an approach has. Next part is, could we squeeze out some extra performance to make sure we don't bring the entire cluster down, or we don't have to force an expensive upgrade? First off, the first thing that we did was not all feature transforms are created equal. And by that, I mean, the first approach was, we've got the status quo model, so let's try and replicate the same features for an MLeap-based model. We didn't need to do that. MLeap struggled with adding a large number of features, but you could do cross products and other things, which are semantically similar features, but they may not be syntactically similar. At the end of the day, they will train your model and give it roughly similar performance. And this is the first thing that we did. You might not have the same kind of features available. There might be some different kind of feature transform that you might want to do, because some feature transforms are inherently, they will run faster than other ones. The other thing that we did was we were a bit unsafe in certain situations in terms of typecasting, making sure that the types were of the right type when going from one stage to the other. We removed some of those cases, got some extra bits of performance. And finally, MLeap is written in Scala. Scala is kind of weird. There are algorithmically the same code can run have vastly different runtime performances. So yeah, there's a lot of trial and error understanding what kind of code runs faster than other kinds. But yeah, putting all of that aside, we were able to get some extra bit of juice out of our MLeap runtime, and we did manage to do it. We managed to do it. Option 2 was launched to production. Engineers were quickly able to prototype and test with not only the new MLeap-based status quo model, but they were able to prototype with a lot of different models really, really quickly. And a model that had basically not been changed for quite some time, they were able to replace it with a faster gradient boosted tree solution. And yeah, this was one of the big benefits of going to this approach. And it was almost a vindication for us that our solution does what it asked for. The other part of it was that because we are an ML infrastructure team, we are constantly focusing on building our model platform out. And so we are adding more feature transforms. We are adding different kinds of models. We are adding TensorFlow-based models as well to our model platform. Again, using MLeap as its runtime. And all of that work directly helps this team, because now that this is deployed, whenever those new models and those new feature transforms are available, our engineers can prototype with them and quickly use them in production. Yep, and that's the end of the talk for me. There are some resources here. You can check out the engineering blog for Yelp. There's a really good post on the model platform by Jason at the engineering blog. As far as our ranking platform is concerned, we're moving from Elasticsearch to NRT Search, which is again an open source project which you can check out. There are also links for MLeap, PySpark ML, and MLFlow. Thank you.
Thanks, Talal. It was really engaging. And I really love your engineering blog, by the way. I'll check out your model platform post too. Before we go to the questions, I'll just remind our attendees that if you'd like to leave your feedback for Talal's talk, please fill out the session poll. And let's see what questions we have. Bushan is asking, can MLeap help some models which are not Spark?
MLeap has support for tensor models. It also has support for scikit-learn models. There are MLeap. One thing to note for those things is that support for all those different projects has varying degrees of support and how maintained they are. So if you are going to adopt one of those, be sure to be ready that you might have to contribute back to MLeap.
Mm-hmm.
Yep.
Okay, and Clinton asks, you said we're moving away from Elasticsearch to something. What was it?
Yes, it's NRT Search.
Okay.
Clinton, you're right. Yeah, it's NRT Search.
And what are the differences, by the way? I'm also curious to learn about it.
So NRT Search is more geared towards online serving, whereas with Elasticsearch, more recent developments are focusing more on analysis. So yeah, and to give you like there's going to be hopefully a good blog post on this. But one of the major differences is how much cost would be associated with when you want to scale a cluster up, and how many, like the size of the cluster that you would need. So there are differences in how it is implemented. It is still based on Lucene, so very similar to Elasticsearch, but it's more optimized for when you want to power your search specifically, as opposed to also wanting to focus on analysis.
Okay. And Bushan has a follow-up question. MLeap serving gives better performance over Python serving. Can you please share more details about how you prefer to serve the non-Spark models with low latency, he asks.
Okay, so the initial part of it is that our everything that we did was like the heavy lifter for us in terms of machine learning is Spark itself, which is why I wanted to use MLeap, because using Spark directly for online serving is just not a reasonable option. So we used MLeap for that. Because MLeap is written in Scala, it's a lot faster than any kind of Python code would be, which was really necessary for us. The final part is for non-Spark models, again, we're using MLeap because we're already using MLeap. So instead of having to maintain something else as a serialization format, it's better to just build on MLeap, which we already know it's a nice, tried and tested solution. So for example, with TensorFlow, we're using MLeap because we've already been using it. And we've had good experiences with it. So there's no reason to adopt something else. But yeah, one of the concerns is that like TensorFlow is pretty well maintained. But if you wanted to use more experimental models, and like there are a lot of platforms for that hold deep learning models, and for those, we might not always be able to support it. But yeah, that's something that you're always willing to give. You're always willing to concede when you're thinking of building a generic platform that you might not be able to support more specific platforms.
Okay. One other question from Jan. Could you disclose what are you inferencing with your models?
Sorry, I don't.
I think he's asking about like what types of models for what are you using? What are you inferencing with your models? What are you predicting with your models at Yelp? I think this is my understanding of Jan's question.
Yeah, we're computing a score to help you the ranking.
Ranking, okay.
Yeah, and you can look up it's ranking. I think it's fine. We're using learning to rank. You can look that up. I think like Prashant asked a question about MLFlow. We use MLFlow for storing metadata for the model. So when you evaluate the model, all of its evaluations are stored directly to MLFlow. And we also use MLFlow for storing the MLeap bundle. So the serialized MLeap bundle gets stored to MLFlow. When we want to get the model back, we again talk to MLFlow to get the model back.
Okay. While waiting for other questions, I have a question of my own. I was wondering, is there anything that you would do differently if you could go back in time when you were first implementing this? Do you regret any decisions? Or was there anything that you, for instance, underestimated as a challenge and it turned out to be more difficult than you had expected? Or would you choose any other thing when you were implementing this?
I think we never expected that we would be that much slower. We thought it would be maybe like 15-20% slower than what the status quo was. We were a lot slower, and we did not expect that at all. Simply because most of our previous experiences were pretty good.
Okay.
Yeah, one of the reasons for us being that much slower is that the feature generation pipeline was pretty sophisticated. There were close to 1,000 different features that needed to be created. And so we were really pushing MLeap's runtime to the limit. If going from one stage to the next, like one way from in your feature pipeline where there's hundreds of stages, if the amount of time that it takes from going one stage to the next is slower by even a little bit, it's going to get amplified by close to 1,000. And so that is something we did not expect. And it took us close to a quarter to actually improve the performance to where it needed to be. Yeah, and for a while we ran the risk of having done a couple of quarters of 3-4 engineers working towards this goal and it not coming to fruition.
Okay, got it. So I think we don't have any more questions. Oh, one more question from Bushan. Yeah, he's asking, we have default Python serving with MLflow, but did you use MLeap so that you have also Java serving?
Yes, we wanted Java serving. Like the whole logic behind using MLeap is we wanted Java serving and we wanted quick serving. Like especially search use cases, you need to be your latency needs to be super low.
Yeah, sure. Okay, let's give.
Yes, we did do it with the help of MLflow. So MLflow helps you create your own flavors, and we basically created a flavor as a wrapper around MLeap. So yeah, MLeap, like with we ask, you can look up flavors on MLflow. We create a new flavor as a wrapper around MLeap, and we just ask for that flavor of model back. And we get it, we get it back, we deserialize it, and we use it. For everything else, yes, absolutely.
Okay. Now I think we have a clear understanding of your architecture and your motivations behind it. Yeah, thanks from myself for answering those questions patiently. And this was a great talk, actually, inspiring to build something similar to ourselves if we need anything. So thank you, Dan. I think we don't have any more questions and we can wrap up now. Thanks, Talal, for your talk, and thanks everybody for listening. Have a great rest of your days.
Thank you.
Thank you.